Right, year 13, let's go. This is the University Grade Prediction Exam, paper 3 that you did recently. So if you remember, this is the Mechanics and Electric Circuits paper. Right, so let's first video, I'm going to run through the 10 multiple choice questions, which I thought all 10 of them were very quite straightforward. Anyway, what we've got here, so a rechargeable cell is labelled. It's labelled 1500 mAh, right? What this might have thrown you, this unit here, mAh, that's actually a unit of charge. Okay, you'll see that written on the side of regular batteries when you buy them in the shop. But milliamp hours is another unit for charge, but it's obviously not the standard unit, because the standard unit is the coulomb. Okay, so milliamp hours. No prize for guessing that. Milliamps. Current times time. So we know that, okay, we know that Q equals IT. So it should be fairly straightforward there. That's milliamp hours is another unit for charge. So we're just going to use the values we're given. So the current is 1500, but it's milliamps, and the time is 1 hour. So that's 60 minutes in an hour, 60 seconds in a minute. That gives us the charge in coulombs, because we've used everything in standard, we've converted everything in standard units. That's coming out as 5,400 coulombs. So the answer is D. Okay, question 2. Ball is thrown vertically upwards with a velocity of +3 meters a second. Right, you might, was what I started doing. I started doing the calculation, but then I realised that all it wants you to figure out is that it's at maximum height. What's the acceleration? Okay, now you should know with all projectiles, acceleration is constant. Acceleration is 9.81 meters per second squared down. Okay, now if we have an initial vertical velocity of +3, the acceleration must be downwards. So it's that one there. So acceleration is constant at all times, even at maximum height. Question 3, which one's equivalent to the ampere? Well, I is Q over T. So the ampere is coulombs per second. C. Over the page, question 4. Right. Weight of 10 grams on Jupiter. Well, let's do it on Earth first. W equals mg. So it's 10 times 9.81. So that is 98.1 newtons. So that's the weight of the 10 kilograms on Earth. We're told Jupiter has a gravitational field strength 2.6 times larger. So on Jupiter, okay, on Jupiter, so WJ, we've got 98.1 times 2.6. So that's coming out at 255 newtons. That's the closest one there, D. Question 6. We've got identical resistors. 6, 6, 6. Okay. There's a parallel bit. There's a series bit to the left. Right, let's do the parallel bit first. So, of that bit there, 1 over 6 plus 1 over 6 is 2 over 6. So, for the resistance of the green part is 6 over 2, 3 ohms. Okay, now in series with a 6 ohm, that's going to make 9 ohms. C. Okay. Over the page, where are we up to now? Question 6. Right, what's equivalent to, okay, the rate of change of momentum. Not momentum, not change in momentum, but the rate of change of momentum. So what we want here is, okay, the rate of change of momentum, okay, the units of, okay, that's actually force, yeah, Newton's second law of motion, that's equal to, equivalent to the force. So we've got, so change in momentum, we've got Well, that's going to be, so we've got mv over t. So we've got, units wise, we've got kilograms, meters per second, then because we've got time underneath, another per second. So that's kilograms, ms to the minus 2. Okay, that's going to be C, isn't it? Okay, remember I said that that's equal to force before? Well, force also equals mass times acceleration, doesn't it? Right, question 7. Question 7. Right, we've got the transport equation. I equals N, okay, Q, V, A. Right, it's a metallic conductor, so it is going to be an ohmic conductor. Okay, with an ohmic conductor, as temperature goes up, resistance also goes up. If resistance goes up, current goes down. That's for any ohmic conductor. Now, in an ohmic conductor, you should also know, well, the cross-sectional area is constant. Okay, the charge on an electron, because these are our charge carriers, that's constant. Okay, the charge carrier density is constant. This is an ohmic conductor. Okay, N does not change. N changes with semiconductors. Okay, so what have we got here? Well, we've got I going down, which means that drift velocity must go down as well, because N, Q, and A are constant. So which of the following quantities decreases? It is C, the drift velocity. Question 8, a ball of mass m strikes a wall. I think a drawing will be in order here so that we get the sign convention right. Now we've got a ball. Okay, so let's take that direction as positive. It's rebounding at the same speed in the opposite direction. Now, and in collision time t, we want the mean force. Like I said previously, okay, the force is the rate of change of momentum. Now the net change in momentum here is mass. Now we've got minus v minus plus v all over time taken. So that's coming out as minus 2 mv over t. Yeah, quite a few of you would have gone with that one by accident, but drawing the diagram like I've done there and taking obviously to the right as positive means that the net change of momentum is backwards. So the answer is D. Okay, because of the minus sign. Question 9, temperature. Right, it's an NTC thermistor. Now with NTC thermistors, as temperature increases, resistance goes down. So let's just map that out first. Always a really good idea in electrical circuits, when resistance is changing in a circuit, I always love to do this. Okay, so it's an NTC thermistor. As temperature goes, try that again. As temperature goes up, okay, yeah, because it says as temperature is increased. So if temperature goes up, resistance goes down. Okay, as resistance goes down, current goes up. Right, now why do, okay, because that's completely the opposite of ohmic conductors, isn't it? What is it about semiconductors that means that their resistance actually goes down with an increase in temperature? Well, it's all down to, if we just get up the transport equation again, okay, like that. Okay, now cross-sectional area is the same. Charge on an electron is the same. Okay, drift velocity may change, but without question, the most significant change with a change in temperature in a semiconductor is that one. Okay, right. We want current to go up. We've just said here, current's going up. So if current is going up, then that's because N is increasing. Okay, we've got an increase in N, and that is D. Okay, and then finally, question 10. Okay, cheeky bit of statics. Here we go. Right now, it is, yes, okay, it doesn't actually say it's in static equilibrium, but even so, it's not, even if it's sliding down the slope, okay, this thing is not moving up or down, okay? This thing is always in contact with the slope, so that means that this component of weight is equal to R. Okay? Now, if that angle there is theta, that angle there is theta. So at all times, if the block is in contact with the slope, R is equal to, well, this is W cos theta because it's adjacent to the angle. So W is equal to, so R is equal to W cos theta. Okay, well, that leaves two of those as options. Okay, but as we know, with cos theta, okay, with cos theta, as theta increases, cos theta decreases. So, as theta increases, okay, it's the normal, yeah, as theta increases, R will decrease because R is W cos theta. Okay, all because as theta increases, cos theta decreases. Right, there you go. There's your multiple choice. I thought they were all straightforward. Thank you.